I actually don't speed a lot. I speed relative to the speed limit.
Okay. Okay, correct answer is E. Okay. It wants to do this. It wants to go to a higher electric potential. And so to bring it to rest, you're doing negative work. There's 100 volts across that. Has a charge of 1 electron. That's where the electron volt comes from.
So basically, if it stopped, like once it reached 100 volts, it was going like full speed. It would have zero to 1, right?
Right. Okay. Give this one a shot. You know what? I should do this. I should do this. So you guys can, oh dear, this is going to be a mess. I'm rearranging it so you guys can see it. Everybody's like, okay.
We're always going to have to lean around people.
I know, well.
I mean, the way you have chairs set up, you have sitting.
I know. I know. Well, check this out.
But now we're going to have to change the other people one.
Like, oh yeah. Alright, let's see.
Is that not better?
Actually, yeah, but I mean.
Alright. We'll give you that one.
Okay.
I'll give you that one. We'll give you credit.
Have a conversation.
And it's yeah, it's gonna go to the smaller ones, the line caps, and the arrows are going this way, so this one. So that's eliminating speed, and then I know that keep going smaller ones are actually properties better. Doesn't that mean it's oh, okay. I didn't know.
Okay, correct answer is beautiful butterflies. I agree. Okay, electric fields always point downhill to a lower electric potential. The closer these are, the steeper it is, the stronger the electric field. Good? All right. Give that one a shot. What do you say?
Boisterous balloon.
Okay, the weird thing is this is 0. You have a positive 50 and a positive 50. Everybody recognize that? It's kind of wacky. I agree with B. Always B. There it is. That's the life hack right there. Not true.
On the SAT, it's B.
Okay. Correct answer. Tell your neighbor. Correct answer is B again. Bountiful buffaloes. Freeze. You don't want to freeze. Okay, next problem. Have a conversation.
It's not that. It looks like that's the way you multiply charge to be able to create normal. Oh, okay.
I'm putting in my calculator so I can just type into it.
It does have to be. No, it's not. It's negative. It's traveling down. It's not.
Don't negative charges go against you.
Yes.
So the external charge is good.
No, the external charge is negative.
Yeah.
Because
Force.
yeah, the external work done is going to be the opposite of what the field is doing, and since it's going to the negative, and the electron itself is negative.
Oh, done by the net external force, not the force.
Correct answer is
It's positive. We don't have.
okay. Find somebody else you disagree with. Find somebody else you disagree with and prove to them that they're right and they're wrong.
Potential energy is increased.
Yes.
Yes. Potential energy is increased. Means the net work has to be negative. Means the net force has to be negative.
No. It is going against the way it wants to go, which means the field is doing positive work. Right? The field is going to show the force.
It's on canvas.
No, wait.
I'll print that out. Yeah.
It's a negative charge goes downhill. A negative charge is which is not the direction you want to go. But there's a force in the direction it's going.
Work done by the net external.
Not every day.
It's positive. If it's work done by the net external.
All right. What do you say? Correct answer is A. Positive work. Okay. It is going negatively charged, wants to go uphill in the opposite direction of the electric field. You're making it move the way it doesn't want to move. Okay, that external force, that those electron tweezers is like dragging this thing. Okay, doing positive work. Good with that? The work done by the field would be negative 1.5 joules. Good with that? Okay. Is everybody, just to like walk you through this, we're still doing force times distance. Okay. We're just making the force the electric field times the charge times the distance. Good? Tell your neighbor. Correct answer is still A. Still 1.5, positive 1.5. Okay. If you are starting and stopping at rest, or you are moving at a constant velocity the entire time, the work done by external force is going to be equal to the work done by the field or the force, the conservative force, just the opposite sign. Everybody good with that? Do not converse yet. Think. Thumbs up when you have a guess. Have a conversation.
Towards the field comes in, it's not like and then it's the electric field goes down.
I'm thinking to change, we can find a change. Yeah, we like work hard.
Like a school. I'm sorry, Pete. Yeah. Magnifying.
Actually, I had it's not boring. It's not boring. I got kids. I'm in the shop.
What do you say?
It's a negative.
No, it's
Good. I like that.
yeah. If the voltage is the hill, then the electric field goes down.
Okay. And we're going uphill. Sorry. Hold on. Electric field points downhill. So B is going to be higher electric potential. No. Out of positive into negative. Sunshine. Okay. All right. So then we get that. I'm going to save capacitors for when we do capacitors. Not that. Like,
You're on the homework. I did already.
does it have capacitance?
Yeah.
Okay, we'll do the homework. All right, we'll do capacitors. All right, here we go. That's a kick. Got a capacitor.
Oh yeah, you wanna unfreeze it.
Good call.
That's a new question.
Is everybody okay with 3 volts?
Yes.
Okay. So Kirchhoff's loop rule. says that the sum of all voltage drops and gains, electric potential differences in a loop is equal to 0. Okay. The voltage gains are equal to the voltage drops. Drops of battery that gives energy. So this, we have a voltage gain here. There's no drop in the wire. So we'll say this is like 3 volts, 3 volts, 3 volts, 3 volts has the electric potential. Here this is 0 volts, 0 volts, 0 volts, 0 volts. So the electric potential difference across here is negative 3 volts, this is positive 3 volts. Voltage gain, voltage drop. Okay. So this sets the stage for the playground, which we find capacitors in. Okay. A capacitor is symbolized by 2 parallel plates. And the very simplistic capacitor is 2 parallel parallel plates, a certain gap, a certain area. Okay. So when we talk about circuits, water flowing through hoses and pipes is a common analogy. Capacitors are like a pressure tank. You are on a well. You have a pressure tank in your house, garage, somewhere, utility closet. The pump feeds the pressure tank. There is a bladder, expandable bladder in here that blows up like a water balloon. This is what provides the pressure for your house. Okay. The size of your pressure tank, that's your capacitance. How much pressure there is, that's your voltage. And how much water is stored in your pressure tank, that is the charge. Okay? So what we're trying to do is trying to hold charge. We're trying to hold water in a pressurized form that's ready to flow when called upon. Okay? That makes sense. So in this case, there's some sort of elastic potential energy in the pressure tank because this bladder has been stretched. With capacitors, we would say we're storing electric potential energy in an electric field. That's common, that's like lingo for a capacitor. Storing electric potential energy in an electric field. Where is that electric field? Between the 2 plates. So, electric field between these 2 plates is equal to the charge on the plates divided by epsilon naught. Okay. 1 over 4 pi epsilon naught. Okay. That thing is we're real heavy here in a second. 4.48 times 10 to the negative. Whoa. What was it? 8.8. That's not. Times 10 to the negative 12?
Yeah. This is just the permittivity.
Yep, permittivity is free space. Okay. So the voltage across that is, because it's constant, is, hey, we've seen this equation before. Okay. Good at that. So capacitance, in a very basic sense, is charge over voltage. It's how much charge you can hold for 1 volt. From a pressure tank analogy, it's how much water, how many gallons of water can be held for like a certain amount of pounds of pressure. If you push in more water, that's going to be, there's going to be more pressure built up. But it's looking at the ratio of how much water there is for how much pressure you're pushing in.
A was area, right?
What?
A is area, right?
A is area. Okay. So I know I'm like dipping into circuit stuff a little prematurely, but this is like, so Ohm's law, okay, voltage is equal to current times resistance. This equation is kind of like saying, looking at resistance in terms of voltage over current. Experimentally, we can measure these. We can measure the voltage across the resistor, we can measure the current going through a resistor, and experimentally we can calculate, figure out the resistance. But in reality, resistance is determined by the geometric constructs, the physical characteristics of the resistor, resistivity, length over the area. Saw that last year. Okay. So this is why something is resistive. Okay. It's like how good of a conductor it is or how good of a resistor it is, the length over the cross-sectional area. This is really why something is a resistor. This equation, why something is really a capacitor. You take the area of the plate divided by the gap distance and multiply by constant. That's not going to change. So this is the physical construct of the capacitor. This we can figure out experimentally, just like we did. We can measure the charge on a capacitor. We can measure the voltage across the capacitor.
For the area, do you add the areas of each plate together?
Beautiful question. No, just the area of one plate. We're assuming they're identical. Great question.
In the case that one
Just
was
that.
If they weren't identical, would it just be like the area of the smaller one?
Smaller plate. Yes, I think I'm okay with it's a mess with the electric field. All that stuff. Sorry, that's sad. Yeah, definitely just do the smaller one. That's a good approximation. Okay. So increasing the area is going to make a bigger bucket. Decreasing the gap distance is going to make a bigger bucket. Okay. where you go with B on that one. Sorry.
Sorry, on the previous one, if they're identical capacitors and they're, which one is more charged? Never mind, I misread it.
Okay. Tell your neighbor. Okay. What do you say? Crazy cat. Okay. So here's a factoid. If you remain hooked up to the battery, the power supply, whatever that is, the voltage across those plates are going to be the same regardless of what you do because of Kirchhoff's loop. Okay? So you could answer these two different ways. One from this set of equations, the other from this set of equations. Okay? So here we're keeping voltage the same. If we are doubling the distance, we're having the capacitance, we're having the capacitance, we're having the charge. Okay? You can also look at it from an electric field point of view. The voltage is staying constant. The distance is doubling. Therefore, the electric field is having. Yep. The area stayed the same. Therefore, you have the charge. Good with that? When I was in your shoes, I would be 100% dependent upon the equipment, especially with capacitors. I did not have a very good intuitive feel of what's going on in a capacitor. I'm going to try to give you that intuitive feel. Okay. So, the fact that you're hooked up to the battery, I don't know how to give you an intuitive feel other than Kirchhoff's. Like that, that's just it. Like voltage gain equals voltage drop. Okay. So regardless of what you do. So that's going to cause, there's attraction between these two plates. Okay. If you put a charge, we'll just say an electron there, there's going to be an attraction to this side and a repulsion from this side. because there's an electric field in there. We separate these two. Ooh, okay. I'm going to give you the conclusion before we give you the blah, blah, blah. Okay. We separate those two. There's going to be less charge able to store on here. I'm seeing if I'm going to ruin a future question. All right. If I separate these two plates, bigger. I look at electric potential difference as in, I compare that to like potential energy, gravitational potential energy. I'll draw it like this. Here's your positive plate, here's your negative plate. An electron here has a certain amount of potential energy here. It wants to go this way. Got that? Because there's a certain amount of electric potential difference. I know I'm totally changing this up here. If I elevate this, I'm doing this, if I elevate this and kept the charge the same, so I did not hook it up to a battery, but it's disconnected the battery, the charge on here is identical. This electron now has farther to fall, and I increase the amount of potential energy there. And I increase the voltage across these two plates, disconnected from the battery. Now I'm changing that scenario. Are you okay with that? Because the electric field in here is constant in between it, regardless of the gap. Depends on the charge on the plate. So increasing the amount of potential energy. How would you want to do that? Okay. Staying connected to the battery, I know I'm fixing this. That can't be changed. So somehow, when I elevate this, the amount of energy stored there, the electric potential difference across these two plates has to be the same. In order to make that true, my electric field has to decrease. Which would be caused because the charge on the plates were decreased. So that we're kind of going backwards. We can do this mathematically, but conceptually we need to kind of start with the fact that the voltage is going to stay the same, but the charge decreased. As you pull these apart. Chicken and the egg, which comes first? Electric. Separate them out. That's going to reduce how much charge it's able to store because these as electrons come off the battery, they store on here, kicking off electrons on this plate, making this positive. Okay, with that. As you pull these away, that force of repulsion weakens. So electrons are able to come back on here, and not as many are stored on here, so it decreases the charge.
Wait till the electrons just float away.
What?
Is that what you're saying?
No, they don't float in the air. They just go. They backfill, like they go back into the battery, back
Oh,
into the
okay.
wire. Okay.
I was like, are these electrons just like?
No. They're stuck in the system of the wire and the capacitor and battery. All right. Woo. That was a lot of. How much time do I have?
6 minutes.
Okay. Shoot. Tell your neighbor.
Yeah. Just kidding. This feels the same, but there's like the slope is the same, right? But there's a greater distance. So then there'd be a greater change. Like you have these plates, you feel you're moving this plate, you feel this. So it's going to be like a greater distance difference. So it should be like 2 in the wall places.
Oh, duh.
No.
Yeah, if B doubles it. I was looking at things that
Yeah.
B doubles will be less half. Of course not. That's double square.
Okay, correct answer is? Dangerous dinosaur. That's fact. The factoid is, if you disconnect the battery, then the charge on here are marooned or stranded. They're isolated. Like, ugh. Okay? So, charge remains the same. So, the gap distance increases, it doubles. Therefore, your capacitance is halved. Half the capacitance, you need to keep this side the same, doubles. That's with these two. Here, the charge stays the same, the area stays the same. Check this out. Electric field stays the same. So if electric field stays the same, gap distance doubles, voltage doubles. Okay, this is going well with this idea of what I was talking about. If you increase the height at which electrons will fall, increases because the gap distance increases. Okay. Mike had a good analogy. So, electric field is equal to the slope of the slide. The slope of the slide is not changing. We're just increasing that distance. So it's increasing the height. Does that make sense? Still the same slope of the slide, but we just doubled that distance, so we've got to go higher. Do that. Okay. All right. Worksheet. Free response due tomorrow. Oh!
We can go to Sushi Town. You just asked.
Okay, this is the calculus version of things. I put the algebraic version on Canvas. But this is like the legit equation sheet. All right.
There's two. How much of the We're still going to be on February 8th. So, somebody you consider Alright, on this problem,